Hi, I'm Shankri here. So today we are going to present about microwave radiation absorber. And before we go any further, let's get to know the members. Our team consists of 4 students, Tan Kian Hao, Lim Junpin, Kashin Kaundar and myself Shankri Manisegaran. So, what is microwave radiation? Microwaves are a form of electromagnetic radiation, that is, they are waves of electrical and magnetic energy moving together through space. Electromagnetic radiation spans a broad spectrum from very long radio waves to very short gamma rays. The human eye can only detect a small portion of this spectrum called visible light. A radio detects a different portion of the spectrum and an X-ray machine uses yet another portion. Visible light, microwaves and radio frequency radiation are forms of non-ionizing radiation. Non-ionizing radiations does not have enough energy to knock electrons out of atoms. X-rays are a form of ionizing radiation. Exposure to ionizing radiation can alter atoms and molecules and cause damage to cells in organic matter. The most common consumer use of microwave energy is microwave ovens. Microwaves have 3 characteristics that allow them to be used in cooking. They are reflected by metal, they pass through glass, paper, plastic and similar materials, and they are absorbed by foods. And have radiation injuries resulted from microwave ovens? Let's see. Most injuries related to microwave ovens are the result of heat-related burns from hot containers, overheated foods, or exploding liquids. Microwave radiation can also hit body tissue the same way it hits food. Exposure to high levels of microwaves can cause a painful burn. 2 areas of the body, the eyes and the testes, are particularly vulnerable to radio frequency heating because there is relatively little blood flow in them to carry away excess heat. Additionally, the lens of the eye is particularly sensitive to intense heat, and exposure to high levels of microwaves can cause cataracts. But these types of injuries, burns and cataracts, can only be caused by exposure to large amounts of microwave radiation. Most injuries are not radiation related. That said, there have been very rare instances of radiation injury due to unusual circumstances or improper servicing. In general, microwave oven radiation injuries are caused by exposure to large amounts of microwave radiation leaking through openings such as gaps in the microwave oven seals. So, in order to address issues induced by high spread of electromagnetic interference in both civil and military applications, efficient microwave absorbers are becoming highly desirable and necessary. For that reason, such material is required to effectively reduce the reflection of electromagnetic signals over a broad absorption bandwidth. In order to improve the performance of microwave absorption properties, microwave absorbers are designed to meet the specific requirements of simultaneously having strong absorption, wide frequency band, lightweight and small thickness. Improvements can certainly be made to the designs by physical assembling of different types of absorbents, chemical decorated absorbents, as well as by designing multi-layer structures. In this video, the microwave detector is used to detect the rate of microwave leakage radiation of an oven. Later, the microwave leakage radiation of an oven with and without the application of the radiation absorber was compared, discussed and analyzed.
Hello guys, today I would like to show you how do we simulate the microwave leakage using the software called CST Studio Suite. So this software is a 2021 version, but I'm using a student edition. And for the microwave simulation, we need to select a 3D simulation with a high frequency setting. So for that, open your CST Studio, go to bottom left, click 3D simulation and then go to high frequency. After that, you need to change the unit setting. So click on units, click the dimension, we are going for cm version, and then for frequency we are going for gigahertz, and then press OK. After that, go to the simulation section, go to frequency, and then we're gonna put 2 GHz to 6 GHz. After that, we go to modeling section and then select the brick. This is where we're gonna put our material. So press exit for you to pop up the dialog box, and then at here we will rename it to material. We're gonna put the size of 20 cm times 20 cm with the thickness of 2 cm. And then for material, click on this, load from the material library, and at here you can search about which material that you want to measure your microwave leakage with. So I'm gonna select air, for example. So we just load it and then press OK, and there you go. There's a block of air there. After that, go to simulation, go to waveguide port, click on it, and here we're gonna put our transmitter and receiver port. So we're gonna put at the Z plane. So for the first one, I'm gonna put at the front. So select Z and select negative. After that, click apply. Then for the second one, I'm gonna put at the back of the material. So change back to positive, and then press OK. As you can see, there are two waveguide port, where one is a transmitter and another one is a receiver. After that, we will change the distance between the transmitter to the material and the receiver to the material. The receiver should be the concept of microwave leakage device measurement. So click background. At here, we will put the distance of 50 cm, 50 cm, and then press OK. As you can see, the transmitter and the receiver distance from the material by 50 cm. After that, we're gonna select our boundaries. So this is our boundary condition where what the waveform will act as. So go to symmetry plane, and here you need to remember about microwave waveform. So for the YZ plane, it should be electric, the XZ plane should be magnetic, and the YZ plane should be the directional. So for this one, we just select none, and then press OK. After that, we can start run the simulation. But before you start run the simulation, you need to check the mesh cell property. So go to global mesh property option, where you can see at the bottom right, show us around 400,000 above the mesh cell. So for our student edition, you can only measure up until 100k of mesh cell. So we're gonna adjust the value based on different type of material that we're gonna measure, and then we're gonna put the setting of 2.5, 10, and 10. Click apply and OK. As you can see, the mesh cell is now 1908. So this should be good for our simulation and then for the rest of the materials. After that, just run your simulation. For this one, you don't need to change anything, just click start. For us to access the result, go to the navigation tree, search for D1 result, and then go to S parameter. As you can see, there's a lot of lines here. We are only gonna refer to the S11 or the S21. S11 will be the transmitter and the S21 will be the receiver. So in order for you to take those results and save it, right click on the S parameter, create the tree folder, rename to result, and then you just move the result. For this example, I will check the S11 only. As you can see, this is the S11. So I'm gonna rename this as the air, because just now we were measuring was the air material. I'm sorry about that. Okay, that should be good. Okay, for you to measure another type of material, simply go to the component, right click on component 1, and then change the material by clicking assign material and color, and here go to the material section, and then you load from the material section. So for the next example, I will click wood, then I will select wood. So we just load the wood. This will delete the current result, but we have already saved our result, so no need to worry. Press OK. As you can see, the results are still there. So this one, we just run the simulation as the mesh value are still good for us to run. After you run the result, so the latest result will be about the wood. So if you want to compare about the result, just move the current result, which is the wood one, into the result file, and then rename it as wood. After that, click the file for you to compare the result.
Hi, my name is Lim Chun Ping. Now I will show and explain how the experiment flow and the result of this simulation. So in the case study, we have to find out a high characteristic of a microwave adsorption material, as it will become our microwave oven cover. So in the software, first we need to make the transmitter and the receiver port in constant value, constant distance, and then we can change the material plate between these two ports in another types of material. So to change the material, we can go to material and then assign it. Then we can load any kinds of material that we want to test. So after that, we can start up the solver and then run the simulation. So as an example, it will give us two different kinds of S parameter in the result. So these two kinds of S parameter is represented for refraction signal and the transmission signal. So we can see it is different reading in the different frequency. So we have to use a curve marker to mark it as to change the position in 2.45 GHz, which represented a microwave oven frequency. So we can take the value of these two in the result. So we can collect it in different kind of material like this. Then we can know. So the result is shown like a table. So we can see the different kind of material have a different kind of adsorption percentage. So we can see that EcoZorb AN72 is a more highest adsorption in this frequency. Okay, so we know that the EcoZorb AN72 is a good material which in 2.45 GHz microwave adsorption. So we can use it to continue the simulation, which we can adjust the distance between the plate and the receiver port Z2. So imagine that this is an internal of microwave oven. It transmits a signal to hit a power, and then the rest is a linkage power that go the outside. So we can test and measure the linkage power in a different distance that we want. So in this case, we are going to measure it in the 10 to 50 cm. So to change this distance, we can go to the simulation and then go to the background, then change the lower Z distance from 10 cm or to the 50 cm. So apply it. As you can see, the distance already changed. So finally we will get a result as like this. Okay, so finally we can get the result in this table. So it will show the result is exactly same in the reading. Then we can get a similar absorption percentage from this simulation. So we can use this 62.7% to the next step of calculation of linkage power from the microwave. That's all from me. Thank you.
Hi guys, I'm Tan. Today I would like to present to you guys about the analysis and findings of the result from our project, which is the radiation absorber. First of all, I would like to present to you guys about the microwave leakage illustration, which can be shown in this figure. So in this figure, we can see that there's a circular shape that surrounds the microwave oven, which is the radiation waveform that produced by the microwave oven itself. D is the distance between the user and the radiation signal from the microwave oven in the direction of AX. For our analyzations, the direction is only counted for AX for our waveform propagations, and then the range of the distance that user they are exposed to the radiation signal is from 0.1 to 0.9, which within this distance is found that the strength of the signal from the radiation will harm the user. So these parameters will be taken into account as our analyzation. For the power rating of the microwave oven, we are concentrating on the Sharp household model, which it has a standardized current rating of 5.8 ampere. The standardized current rating will be then used for the charge calculation. For the charge calculation, we assume that the charge will not affect any of the parameters in our next calculation, which the charge will be static throughout all of the experiment. The formula of the charge is Q is equal to integration of time limit according to the standardized current rating. So for our time limit, we assume that the time is from 0 to 30 seconds, and we integrate the answer, we get 174 coulombs for the charge. After that, we are going to analyze for two of the conditions. The first of the condition is the condition that without the radiation absorber. Initially, we obtain the power of the losses is around 500 to 900 milliwatt, which this will be used for the next calculation of the electric field of the radiator wave, which the E is the formula is SERT2 W divided by epsilon naught, and then the obtained value for the E can be used for the calculation of the flux density, which is D is equal to epsilon naught times with the electric field. Okay, before we start our analysis for the second condition, there are several S parameters that we are going to determine for our material, which is the EcoSwap at N72. So the S11 is the S parameter of reflection, S21 is the S parameter of transmission, and then the input will be identified as 100%. So with all of these parameters, we will use the formula as below, which the absorption value is equal to 1 minus S11 square minus with S21 square, and then we can also get the absorption percentage from the previous value, which we use the previous value to multiply with 100%, and at the end we will use the formula of 1 minus absorption value minus with reflection value times 100% to obtain for the transmission value percentage. So when all of the parameters of the EcoSwap at N72 are calculated, and is tabulated as in this figure, as the highlighted row, we can see that the EcoSwap at N72 material has the highest absorption rate, which is around 62.7%, and the transmission signal is around 0.19 x6, and is then used for the next calculation for the second condition. So this is the second condition, which the condition with using the radiation absorber. So when we use the radiation absorber, there is the changes in the electric flux density, which the d nu is equal to d naught times the percentage of transmission value that we obtained previously. Then For the d nu value, we will use for the calculation of the new electric field, which E is equal to d nu divided by epsilon naught, and then the new E value we will use for calculation of the new power leakage, which W is equal to 1 over times with E squared times with epsilon naught. When all of the stuff has been calculated and is tabulated and compared with each other, so this is the first part of the data, which is the data that we are not using any of the radiation absorber. So from this data, we can see that the detected leakage power is the highest when the distance between the user to the radiation leakage is the closest. And the electric field and electric flux density show a decrease when there is a decrease in the power leakage. However, for the quantity charge, it remains the same at all times. So this is the second data result that we are going to compare with the previous data. So this is the condition that we are using the radiation absorber. So from this result, we can see that there's a significant changes of the leakage power, which the power has been decreased from 900 milliwatt previously to 360 milliwatt currently. And then the electric flux density and the electric field also show a decrease in the trend. And for the quantity of the charge still remain the same. So after that, we will also discuss about the percentage error of the maximum power loss. So the maximum power loss for the condition without absorber P0 is equal to 900 milliwatt. The percentage power loss for the condition with absorber P absorber is equal to 360 milliwatt. So from there we can calculate for the percentage error of the power loss for two conditions, which the answer is around 60%. So this 60% indicates that the power loss of the initial condition has been decreased with a 60% rating to the current power loss value. So with all of the data we have in the table, we can plot the graph of electric field against power loss when radiation absorber is applied. So from this graph, we can see that the electric field is directly proportional to the power loss. When the electric field decreases, the power loss is also decreased. Secondly, we will also plot the graph of electric field against the electric flux density when radiation absorber is applied. So the electric field is again directly proportional to the electric flux density. When there is a decrease in the electric flux density, there will also be a decrease in the electric field. So from our findings, there are two things we can discuss. First is the rate of the absorption of the material used in designing the radiation absorber will affect the transmission rate of the radiated signal. The higher the rate of the absorption, there will be a lower the transmission rate of the signal to be penetrated. So it's very important for us to have a high absorption material to be selected for our absorbing material to absorb the unnecessary signal. Second is the rate of the transmission will affect the strength of the power loss, the electric flux density, and the electric field of the produced radiated signal. So when the rate of the transmission is high, the strength of the power loss and electric flux density and also electric field will be high as well. So it's very important also for us to increase the rate of the transmission in order for us to have a less level of the power loss, electric flux density, and also electric field that produced by the radiated signal. That's all.
Moving on to conclusion. If microwave ovens are used while broken or altered, it is possible for them to leak electromagnetic radiation. Microwave radiation leaks are hard to detect because you can't smell or see microwaves. Microwave oven radiation injuries are only caused by exposure to large amounts of microwave radiation leaking through openings such as gaps in the microwave oven seals. So a proper maintenance would avoid these problems. Based on the results obtained through the study, it can be said that the presence of radiation absorber does reduce the power loss of the radiation leakage. So, we know that the radiation absorber played a role in minimizing the power loss of the microwave oven by decreasing the propagation of the radiating wave. It can be concluded that rate of absorption does affect the transmission rate, whereas the rate of transmission affects the strength of power loss, electric flux density, and electric field of the radiated signal. That's all from us. Thank you.